All right. Good morning, everyone. How are you all doing today? Good. All right. Cool. All right. Does anyone have any questions before we get started? All right, sweet. So we are right here in the semester. So our first exam is 1 week from today. Remember that there won't be any class on Wednesday. Instead, the lecture just will be the exam, which will be at 6 p.m. in Jennings Hall, room 1. You want to arrive about 10 minutes early. That way you can get settled. There are going to be announcements that are about 5 minutes before we start, and then we'll get started at 6. It will be on paper, so you need to make sure that you bring something to write with, because it'll all be on actual paper. You can have something to drink. You can have a quiet snack with you. You need to bring your ID with you, because you'll turn in your ID in order to get the exam, and then you'll turn in your exam to get your ID back. You can have your molecular model kit with you. Everything else will be confiscated. Yeah. Are there any questions? Yeah. Yes, I will still have the office hours that day. Mm-hmm. Any other questions? Okay, cool. All right. Another quick reminder, your next survey is due on Friday. So due in 2 days. Remember, they only take a couple minutes to complete, but you still got to do them, and you got to do all of them. So make sure you get that done by Friday. That'll be your pre-exam 1 survey. So has to get done by Friday. Then there is no quiz this weekend. Okay, that was weird. There is no quiz this weekend, but your homework is still due this weekend. So there's no quiz because of the exam, but you still have to get the homework. That way you have the practice in so that you're ready for the exam. All right. Cool. All right. Oops. Then let's finish chapter 5, or at least get as far as we can through it. So this is the last structure. You theoretically finished it already last class. The top atom is going to be S. So the way that we do this is you have to go atom by atom until you find the difference. So we have hydrogen up top, then I get carbon, carbon, carbon. So that's what you can see that I wrote out here is I get carbon, carbon, carbon. There's the left carbon, the right carbon, and the carbon going down. Off of the carbon to the left, I get 2 hydrogens and another carbon. So I wrote those attachments. Off the carbon to the right, I get 1 hydrogen and essentially 2 carbons. Going down, I get my 1 hydrogen and 2 carbons. So that immediately marks the one to the left as 3, but I still have to figure out what to do with 1 and 2. So when I look at 1, what came off of what ended up being position 1, so this was that first carbon. This is the carbon of the double bond. When I consider what's coming out from that, I do still consider the double bond and the next bond. So this carbon has 1 hydrogen and 2 carbons coming off of it, and then you consider it double because we'd considered the double bond as double. Then when we went down, we got carbon and carbon. You get 2 hydrogens and only 1 carbon. So this is where we're seeing that difference of that double bond is taking the higher priority. So when we connect 1 to 2 to 3, that is going to be clockwise, but the lowest priority is on the wedge. When the lowest priority is on the wedge, we flip it, so that's why it's S. Does that track? Does that make sense? Okay. The bottom one should hopefully have been a little bit easier to assign. So for that one, we again still have the hydrogen, carbon, carbon, carbon. So the hydrogen is going to be number 4. The carbon to the left has 1 carbon, 2 hydrogens coming off of it. Carbon to the right has the 2 hydrogens and 1 carbon. The one going up has 2 carbons and 1 hydrogen. So immediately I know that the top one is going to be number 1. I know that that is going to be the highest priority because that gets 2 carbons. Then, as I walk down from the left, I can see that I'm going to still do CH2, CH2, CH2. When I go to the right, I get CH2, C double bond, so that counts as an extra carbon. So that's going to make the one to the right a number 2, the one to the left is a 3. And then when I connect 1 to 2 to 3, that is clockwise with the lowest priority on the dash, so that does stay R. Cool? Any questions about assigning RNS? Yeah. Sure, go ahead and name that thing. Bless you. So hopefully you got 1s6r440 bicyclodectuene. Any questions about naming that? Mm-hmm. I'm sorry, say that again? Okay, all right, cool. What's up? Yeah, okay. All right, so our stereochemistry, that's what's all the way out front. To actually name the bridge, or our bicyclic system, remember that you must always start on one of your bridge heads. That must be number 1. Then you're gonna head down the longest bridge. So you must go down the longest bridge. I go bridgehead, 1, 2, 3, 4, bridgehead. This is a 4 carbon bridge. To the left, I get bridgehead, 1, 2, 3, 4, bridgehead. So that's a 4 carbon bridge. Then bridgehead, bridgehead, that's a 0 carbon bridge going down the middle. That's why I got my 440. So when I'm numbering, I have to go down the longest bridge, meaning I have to go down the left or the right side first. I'm going to want to give a primary functional group the highest priority. There is no primary functional group, so we just skip that rule. Then we're going to try to give our double bond the next smallest number. So that means that I would need to start as close to the double bond as possible and then number out. So that would be 1, 2, 3, 4, 5, 6. Then I would continue to left, 7, 8, 9, 10. That's how you would number the bicycle. So we get the 440, bicyclo because it's a bicyclic system, dec because there are a total of 10 carbon atoms, including the bridgeheads. So remember that our total is always going to be 2 plus whatever is the sum of those numbers in brackets. That's the dec. Then my parent functional group is an alkene. I need to say where the alkene is located, so it is a 2-ene. The only reason why I don't need to include the stereochemistry here is because that is the only way to get that alkene in that ring is if it is cis. So if you wanted to include it, it wouldn't necessarily be wrong. You just would say 1s, 2z, 6r. You would have to use the z nomenclature because you have chiral centers. So you wouldn't be able to use cis and trans. You would have to use just the single letter code. So if you included it, that wouldn't be marked wrong. It's just not necessary. Just like how if you wanted to include a 1, it's not necessary, but it wouldn't be marked wrong. Cool. Yes. Number 1 can't be the double bond because when we are naming our bicyclic systems, that first rule that we have to follow is that you must start at a bridgehead. So one of your bridgeheads must be number 1. It's that weird thing about our bicyclic systems. Yeah. So you really shouldn't put the 2 before dec because of the fact that we have the bicyclo. So you shouldn't separate the bicyclo and the dec unless you're putting the bracketed numbers in. Really, I recommend always get in the habit, put the number directly next to what it's describing. It'll make sure that you don't make those kind of silly mistakes. Yeah. It's if you're in a ring, there is no way for it to be trans. So if you're in a small ring, then it like the ring can't close in a trans conformation. Like if you try to draw that trans alkene and then you're trying to connect the other 2 carbons, like that can't reach. The bond angles are just too distorted. The first time that you can get a trans alkene in a ring is, I think it's like a 12-member ring. Like you need a large ring in order to be able to have a trans alkene. Any other questions? Yes. Yeah, trans is 1 up, 1 down. Yeah, when they're going in opposite directions. Yeah. Would that same what? So the same thing, so E would also be the same consider. Oh, I see what you're saying. If this was a substituted ring, so, let's see. Yeah, sure, something like that. Again, you still wouldn't need the stereochemistry because the only way to have the ring close is when it's like that. But if you wanted to include the ring or the stereochemistry here, then you would have to say E. But again, the stereochemistry wouldn't be necessary because it's in a small ring. Any other questions? Yes. So superimposable means that it can go on top of each other. Non-superimposable means it doesn't. We're about to get into our enantiomers and diastereomers. We're about to explain that. Okay. Are there any other questions about naming or bicycles? Okay, then let's get into our chiral molecules. Let's talk about what that means. Because you're right, we've kind of been throwing that word around without actually explaining it fully. So our chiral molecules are going to be things that have that non-superimposable mirror image. So superimposable meaning if you slide it over, that they don't fit perfectly, right? So if I have like this and that, like these are mirror images. Like the alcohols are pointing closer to each other, the alkenes are farther away from each other, like those are mirror images. So when I flip one of them, so if I flip this over like a pancake, so that now most of the attachments are all matching each other, right? So the alkenes are now both on the left-hand side. So the rings match up. What I see is that I don't get exactly the same stereochemistry. So when they slide on top of each other, it's not that perfect match. So they're non-superimposable mirror images because they are mirror images where when they reflect exactly, but when you slide them over on top of each other, it doesn't work. So those are non-superimposable mirror images. That's going to be our chiral molecules. You need at least one stereocenter in order to have a chiral molecule. There are two exceptions to that rule to be aware of. The first is going to be our allene. So our allene is a cumulated diene. So when we talk about our alkenes in like a month and a half, we will bring this back, actually probably 2 months, we'll bring this back in. But the reason why is because remember those p orbitals have to be perpendicular to each other. That forces these substituents to also be perpendicular to each other. So you get this like propeller going on where you have some that are going to be pointing straight out and in, and some that are going straight up and down. And so then it's going to act like a tetrahedral molecule with 4 points. So it's going to act like a propeller where it can spin and it'll be able to rotate light. And so it's going to be this locked conformation that can spin. Same thing happens with our binaphthalene. So naphthalene is this two benzenes fused together. It's just its name. So binaphthalene is where you have two of them. So it again is acting like this propeller, where it's like they're kind of, actually I guess it's more like this, where one's going this way, the other's going this way, and then they're going to be able to spin light because they can't go past each other. So it just spins like a windmill, like how a windmill, if you blow on it and it spins, it's the same thing happens, but it's going to do that with our light as opposed to wind. So these are the two exceptions. There are 0 chiral atoms in these molecules because they're all sp2 hybridized. And you cannot have a chiral atom that is sp2 hybridized. You must be sp3. You need to be tetrahedral to have a chiral atom. So these are the weird exceptions. So normally, we're going to say you need to have chirality at the atom level in order to have chirality at the molecule level. If you have only one stereocenter, then you are a chiral molecule. If you have one chiral atom, you are a chiral molecule. That's it. If you have more than one, then you may or may not be chiral. You will be chiral if you do not have an internal mirror plane, if you do not have symmetry. If you do have symmetry, then you will be meso. A meso compound is an achiral molecule that has chiral centers. So it's a molecule that has a chiral carbon and an internal mirror plane. That makes you meso. So in general, if you have chiral atoms, you will be a chiral molecule, unless you are meso. So normally it is, yes, you have chirality at the atom level, yes, you have chirality at the molecule level, unless you are meso. And then you lose chirality at the molecule level. So we need to look for our different types of symmetry. So rotational and reflectional symmetry are where students usually get mixed up. Rotational symmetry, that's where I am essentially flipping something over like a pancake. That is not going to affect chirality. that does not change whether or not my molecule is chiral. This is the same molecule because all I did was flip it over like a pancake. So this is chiral. So rotational symmetry, flipping it over like a pancake, does not change chirality. Your molecule is still chiral with those chiral atoms. Where you get the loss of chirality is with reflectional symmetry. That's where the left and the right side look the same. So that's where you get that internal mirror plane. So any molecule with an internal mirror plane is going to be achiral. If it has a chiral center, then it is meso. So when I look at this, the left side and the right side look the same, right? So if I flip it over like a pancake, this is still the same molecule, right? Because all I did was flip it over. But that isn't changing anything. What I'm seeing, the important part, is when I look within the same molecule without trying to change where it's positioned. I'm just looking down the left and the right side of that molecule. The left and the right side are the same. So that is my symmetry. So these molecules, well, this molecule, because it's the same one, is achiral, not chiral, and it is called meso because it does have chirality at the atom level, but it lost it at the molecule level because it has that internal mirror plane, because the left and the right side look exactly the same. The methyls are on the same side. Whereas when I look here, one methyl is down, one methyl is up. Now the left and the right side are not exactly the same, right? So we're going to practice, try to figure out if the next molecule is chiral. All right, who thinks the molecule is chiral? Who thinks the molecule is not chiral, achiral? Okay, the molecule is not chiral. Try to prove to yourselves why. Remember that you can rotate your structures. So you need to have the left and the right side look the same to see if it has a mirror image. I liked your explanation, though. All right. So what we need to do is rotate around that central bond. Well, actually, the first thing we have to do is ask ourselves, do we have a chiral atom? Because if I don't have a chiral atom, right away, the answer is just no. I'm just done. So do I have a chiral atom? Yes. I have 2 chiral atoms. So if there was only one, then I could really easy just go, yes, the molecule is chiral because there's just one chiral atom. Yes, it is a chiral molecule. But I have 2. So when we go down, we got to check for symmetry. So then I need to rotate around that central bond to get it to be in the eclipsed conformation so that the 2 sides look the same. So when I rotate that down, I get this as my core because I get this to come down like that. This top carbon remains with the wedge. This bottom one, because this is the one that I rotated, now that dash is going to become a wedge. Because it's like it's pointing away, and then I rotated it, and now it points out at you, right? So it goes down, and then points at you. Now it's easier to see that there is that internal mirror plane, where the left and the right sides do look exactly the same. So this is a meso compound because we answered yes to the atom level, but then we had that internal mirror plane that made it meso. So no, it is not a chiral molecule. It is an achiral molecule, a not chiral molecule. Because we've got to remember that we can rotate our sigma bonds. Oh, yes? Wait, say that again? So it doesn't work diagonally. So if you're trying to go this way, like this way, the left and the right sides aren't exactly the same. Like I have a carbon up here, there's no carbon up here. Then the OH is on a dash down here, the OH is on a wedge up there. So the left and the right sides don't look exactly the same. So you did have to rotate it in order to see that symmetry. Any other questions? Yeah. Yeah, we just rotated half the molecule so that the left and the right sides look the same. But if we had had this structure, this one is chiral. Because when I rotate around that sigma bond, now I see that the left and the right sides are not identical, right? When I get the carbon bonds, the lines to be symmetrical, I see that my wedges and dashes stop being symmetrical. Cool. So that is meso. So normally, if you have chirality at the atom level, you get chirality at the molecule level. That's the normal thing. Is yes, you have a chiral atom, yes, you get a chiral molecule. The exception is if you have this internal mirror plane, in which case then you are meso. So that's the weird thing. Meso is not normal, it's weird. Normally, it goes yes atom, yes molecule. Unless you have the internal mirror plane, then it's no meso. When we look at the relationship between our chiral molecules, we get our enantiomers and diastereomers. So the enantiomers are the pair of molecules that are the non-superimposable mirror images. So each chiral molecule gets one enantiomer, regardless of the number of chiral centers there are. Regardless of how many chiral carbons you have, you get one enantiomer. Well, you have to have one chiral center, I guess I should say. It needs to be a chiral molecule. So how to draw your enantiomer? There are kind of a couple different ways. Either you just say, all right, I'm going to keep all of the lines the same. So I get this benzene, and then I had a CH2, and then another carbon, and then the amine. So my lines all stay the same. But now, what was the wedge becomes a dash. What was the dash becomes the wedge. Those are enantiomers. If I keep the lines the same, but I flip wedge to dash, dash to wedge, that'll be my enantiomer. That is inverting that chiral center. The other way is actually just draw the mirror image, which is going to be you keep your wedges and dashes the same, but I'm going to flip my lines. So now what's on the left-hand side goes to the right-hand side. What's on the right-hand side goes to the left. The wedge stays the wedge, the dash stays the dash. That's how you're drawing the mirror image. Do not flip both. If you flip both, the dashes and the wedges, you just drew the same molecule in a different way. You just flipped it over like a pancake. This is the same molecule. Right? That's that rotational symmetry. That is, I just took it, flipped it over like a pancake. It is the exact same molecule. In order to get the enantiomer, you either flip the wedge and the dash, keep all the lines the same, or keep wedges and dashes the same and flip your lines. That's how you draw your enantiomer. To draw your diastereomer, you're going to flip some, but not all. So your stereoisomers that are not mirror images are the diastereomers. You must have at least 2 stereocenters. You must have at least 2 chiral carbons in order to do it, because you need to flip some, but not all. So when I look at this, if I go from left to right across the top, how many stereocenters did I invert? 2, all of them. So what is the relationship across the top? They are enantiomers. Because I flipped that alcohol from a wedge to a dash, and I flipped the chlorine from a dash to a wedge. I inverted all of my stereocenters, so that made an enantiomer. All right, what if I'm going down, bless you, the left-hand side? So my alcohol stays the same, but I inverted the chlorine. What is that relationship? Diastereomers. What if I go diagonally? So I inverted the alcohol from the wedge to the dash, but I kept chlorine the same. What is that relationship? Diastereomers. I inverted some, but not all. How about going down the right-hand side, where now I kept the alcohol in a dash, but my chlorine went from a wedge to a dash? Diastereomer. Because I inverted some, but not all. All right, what about across the bottom? What's that relationship? They're enantiomers. Because I again inverted all of them. My wedged alcohol went to a dash. My wedged chlorine went to a dash. I inverted all of them, makes an enantiomer. The point I'm trying to make here is in order to know if you're looking at a diastereomer or an enantiomer, you need to see what the two molecules are that you are comparing. Because the diastereomer of each of the enantiomers made a new set of enantiomers, right? So you need to have a point of reference. You need to know what are the two things you are comparing in order to be able to assign an enantiomer or diastereomer. You got to look at the molecules that you're actually comparing. All right. Are there any questions about enantiomers or diastereomers? All right. Our Hayworth projections are mostly just used with cyclic sugars. They show up in chapter 24. They come back in Orgo 2 and Biochem. They're very popular in biochemistry. Basically, what it's trying to do is it takes this ring and we're just tilting it. So instead of looking at it planar, we're like, oh, let's look at it like this. So that then you get the lines that are straight up and down to show you that everything that's on the top is going to be the wedge. Then everything that's down below becomes a dash. And so that's just it. That's how you look at the projection. It's just what's on the top would be a wedge, what's on the bottom would be a dash. Our Fischer projections, unfortunately, are not as easy. So our Fischer projections, this might be too colorful. We'll see how this goes. All right, these are mostly used for acyclic sugars, not cyclic sugars. The thing to keep in mind is that all of the vertical lines represent dashes, all of the horizontal lines represent wedges. You must be in the eclipsed conformation. So it's forcing your eclipsed conformation because it's forcing you to have this U shape because it's saying that all of the bonds are going back and down into the plane. So it's forcing that U shape. So all of your vertical lines become dashes. All of the horizontal lines become wedges. You get like the bow tie effect. The way that the book recommends doing it is that you're going to take this molecule and you're going to turn it up and then you flip it out so these are now pointing out at you and then you tilt this back to make it the dash. Personally, I don't think that makes a lot of sense. Like I don't even really know how to explain that to you because I don't get it. So what I find easier is instead of trying to do this weird manipulation of the structure, I'm just going to move myself and I'm going to reposition where I am relative to the structure. So I'm going to instead imagine I am laying on top of this molecule. So I am now on top of the molecule looking down. So now I see, D is above my head. C is down by my feet. B is on the left-hand side. A is on my right-hand side. And I find that easier is to imagine, instead of trying to imagine that I'm like doing this weird manipulation to rotate the structure, I think it's easier to just imagine if I'm above the molecule, where is everything in relation to me? So then remembering that anything that is on the vertical, that dashes, just gets a normal vertical line. Anything on the wedges now become the horizontal lines. So then if I'm just trying to now go from my Fischer to my line diagram, I'm like, cool. That means I'm going to be standing on the side of this structure. I'm now looking at it from this side. So that D is now on my right-hand side, C is now on my left. The A is coming out at me as a wedge, whereas B is going away from me on the dash. That's what I think is easier. All right. I'm seeing some confused faces, so I'm going to try to do it with the document camera. Oop, too much. Yeah, no, that's fine. Okay. Okay. We'll do it this way. All right. So if this is my original structure that I'm imagining, so that C is blue, D is black, A is green, and B is white. All right, so I'm going A, B, C, D. What I'm trying to do is I'm going to imagine that I'm laying on top of this so that I am laying on it where my head is here. And then what I'm trying to do is essentially just flatten this out to get that normal plus sign. So that now D is straight up, my C is straight down, I have A on the right-hand side and B on the left-hand side. So then when I'm trying to now imagine it like I'm over on, on that right-hand side of the structure, I let it relax back so that these are pushing away from me. These are coming up at me, and I'm now going to position myself on the right-hand side so that I am now putting it down like that. So that again, my D is on the right-hand side, black is on the right-hand side, C is on the left, blue is on the left, that A is pointing at you, and then B is going away from you. So like that's all we're doing is essentially just taking it here and flattening it out to get, that's the Fischer projection. Is just trying to draw it faster, and it's going to show us our chirality specifically of sugars is where it's really useful. Does that make more sense that that is flattening? Okay. All right, I see some people, like hopefully that clicked a little bit better. Remember, you are allowed to have model kits on the exam, and you are allowed to have pre-built structures for the exam. So, I mean, you can't share them, but if you have like just generic chiral center built and a generic ring built, then you can do this where you're like, okay, so then I'm going to say, all right, this is A, that's B, and then I flatten it out, and then that lets you immediately see what the Fischer projection should be, right? Okay. Yeah, no, that'll be fine. So that is the Fischer projection, is just trying to make it easier to see these complex structures, to draw them quickly. When you're trying to do it for the complicated structure, make sure you are in that eclipsed conformation, because I need to have my carbon bonds aligned with each other so that when I draw them, they're going to become those dashes going away from me. So I'm going to imagine that I am laying under this structure like this, looking at that structure. So I'm laying under it. And what I see is I have the methyl above my head. I have the aldehyde by my feet, right? And they are going away from me, so that becomes the straight line on the vertical. Now, by the methyl, I see that that hydrogen, which was originally the wedge, is now going to be on my left-hand side when I'm positioned under that structure. So the hydrogen is on the left, your amine is on the right. The alcohol is on the left, the hydrogen is on the right. So that red bond is that vertical bond, right? That's the perspective that we're taking. Cool. So the Fischer projections must be eclipsed. What's up? So you just make sure that the eclipsed bonds are going away from you, but I could have been laying underneath of it like this way. So if I lay under it that way, I again still just have the eclipsed bonds are going away from me. That's the bare minimum requirement. But now I get my aldehyde by my head, the methyl by my feet. Now that alcohol that is closest to the aldehyde, that is going to be on my right-hand side. The hydrogen's on the left. Then my amine is going to be on the left-hand side, and my hydrogen's on the right. So you can take either perspective as long as you meet the requirement that the eclipsed bonds are going away from you. Cool. And it's just, that's the definition of a Fischer projection, is that is the assumption you are making, is that if you're trying to draw a Fischer projection, you are assuming that you are defining it so that your eclipsed bonds are going away from you. That is just the requirement of the projection. And the idea is just to draw the structures really quickly. The relationship between our Fischer projections is such that if you rotate 3 of the substituents, but keep one of them the same. So I did bromine went to the right, the methyl went down, then the ethyl came up. So each of these moved over 1 step, but the hydrogen stayed the same. So I rotated 3, but kept 1 the same. That is the same molecule. If I flip everything 180 degrees, so that what was on the left goes to the right, what was on the right goes to the left, what was on the top goes to the bottom, what was on the bottom goes to the top. So I flipped everything 180 degrees, then that is also the same molecule. That's the same situation as I flipped the lines and the wedge and dashes, right? It's like you're flipping it over like a pancake, essentially. So that is, you're changing the vertical and the horizontals. That is the same molecule. If you rotate all 4, so that now bromine went up to the top, hydrogen went down to the right, methyl went down to the bottom, and ethyl went to the left, this is going to be your enantiomer. And actually, all 3 of these will be enantiomers. That is going to invert your stereochemistry. Also, if you flip just any 2, just like how if I just flip my wedge and my dashes, or I just flipped the 2 lines together, if I flip any 2, but keep the other 2 in exactly the same location, that also makes the enantiomer. So in this case, I kept hydrogen and ethyl the same, but I just flipped my methyl, my bromine. That made the enantiomer. If I keep hydrogen and bromine the same, but flip my methyl and my ethyl, that also makes the enantiomer. It's any 2 get flipped, that becomes the enantiomer. That inverts the stereochemistry. We can always check ourselves by assigning R and S. To assign R and S, if the lowest priority is on the vertical, remember that verticals are dashes, then your clockwise is R and your counterclockwise is S because the vertical are dashes. If the lowest priority is on the horizontal, where we remember all of our horizontals are wedges, then now it flips so that now your clockwise is S and your counterclockwise is R. So if I go to assign stereochemistry of this, for this first one, I see that my bromine is number 1, the ethyl will be number 2, the methyl is 3, the hydrogen is 4. So right now, my lowest priority is on the vertical on the dash. When I connect 1 to 2 to 3, that is counterclockwise, that is S. So this first molecule is S. To prove to myself that this is the same molecule, I can assign R and S. Again, my hydrogen is on the dash. So the hydrogen's on the vertical on the dash. I go 1, 2, 3. When I connect 1 to 2 to 3, that is still counterclockwise. That is S. If I flipped everything 180 degrees, I still see that the hydrogen is on the vertical on the dash. So I can go 1, 2, 3. I see that is also counterclockwise. That is S. So I did maintain my stereochemistry when I rotated just 3 or flipped everything 180 degrees. If I rotated all 4 90 degrees, so each one just moved over 1 position, the hydrogen is now on the wedge. It's on the horizontal on the wedge. So it's going to flip my counterclockwise and clockwise assignments. So I go 1, 2, 3. This is counterclockwise, but my lowest priority is on the wedge on the horizontal, so I flip it, and that becomes an R. I now have my enantiomer. For this structure, again, I'm going to go 1, 2, 3. My hydrogen is on the dash, so it's going to be on, or it's on the vertical, so it's on the dash. When I connect 1 to 2 to 3, that is going to be clockwise, so that is R. That confirms, yes, it was the enantiomer. When I flipped the other 2, hydrogen on the dash, I go 1, 2, 3. I connect 1 to 2, 3. That is clockwise. That is also R. So that is the enantiomer. So I can use the R and S assignment to confirm to myself that I did actually either not change or, in fact, change the stereochemistry, right? Depending on what you're trying to do. If you want the enantiomer, then you want to flip it. If you don't want the enantiomer, then you will either rotate 3 or flip everything 180 degrees. Cool. Any questions about Fischer projections? They usually require like practice with an actual model kit. Like for context, it took me until I had taught organic 3 times for it finally all of a sudden to click where I was like, oh my gosh, I can just look at it and I see the Fischer projection, like for it to become fast. So that was, I lived organic, did Orgo 1, Orgo 2, and then taught it not once, not twice, but 3 times. And then I was like, holy crap, it finally makes sense. So if it doesn't make sense to you, don't worry. It's a weird, hard manipulation. Use a model kit until it gets easier. All right, we'll do the physical properties on Friday. Have a wonderful day.